Hello, my name is Aaron from Pittsco Education. Today, we're going to build a FABLE robot that points north. This project challenges you to learn how to map data to different ranges using math functions and how to plot data using the graphing function built into FABLE Blockly. So let's get going. First, let me quickly show you how to build the robot. We'll use the FABLE base, two 4xy construction modules. I'll also use two joint modules with the button facing up. That allows the X servo to move side to side and the Y servo to move up and down. Finally, I'll add a couple of 3D printed components as well. And then, to top it off, my phone holder. Now, let's transition over to the program. You can download the code for this robot from our website. Simply navigate to pittsco.com/fable and select either the Hello set or the Hello class set. The code is available in the download section of the product's detail page and is titled Sample Code. Click on the box to download and look for the code titled FABLE Points North. Now, let me walk you through the code. The code starts by declaring a variable called angle. A variable is just a place where we can store some information. To start, I'll store a value of 0 in the angle variable. Then, I have a repeat while loop so that the program continues to run until I stop it. Inside this loop, the expression iris color and eyelid color of the FABLE Face app are set. Next, I'm going to change the angle variable to a value read from the phone's magnetometer, or compass. The compass returns a value between 0 and 360 degrees, depending on which direction the phone is pointing. North is 0, east is 90 degrees, south is 180 degrees, west is 270 degrees. We also have this weird equation that multiplies the magnetometer reading by a scalar value of 0.1 and then adds that to the product of 0.9 and the old angle value. All this equation does is gradually, instead of instantly, move the angle value to what the magnetometer reads. We'll see this in action in a bit as we run the program. Now, the phone's magnetometer has a range of 0 to 360 degrees, but our joint modules have a range of only 180 degrees. This is why we'll use both joint modules. The right joint module will point for angle measurements less than 180 degrees, and the left joint module will point for angle values between 180 and 360 degrees. To do this, we use a conditional statement that says if the angle is less than 180, then the right joint module will point north, and the left joint module will point down. Otherwise, the left joint module will point north, and the right joint module will point down. Let's take a closer look at my move statements. Remember that the joint modules have a range of motion of 180 degrees, but the acceptable values are negative 90 degrees to positive 90 degrees. To map the magnetometer range of 0 to 180 degrees to the joint module range of negative 90 to positive 90, I just subtract 90 from the angle variable. Now, when the magnetometer is between 180 and 360 degrees, I'll have the other arm move. To get this range into my negative 90 to positive 90 degree joint module range, I'll subtract 270 from the angle measurement. The final two blocks in my loop will plot the magnetometer value and the angle value on the graph. This will help me visualize my data as I run the program. Speaking of which, let's do that now. Let's run the program. Notice how the robot points north. As I rotate the robot, he continues to point north as I rotate him, until the robot gets to the point where he's facing south. Once he's facing south, he switches arms, and the other arm takes over, pointing north. And he'll continue to point north as I rotate him all the way back around, back to where we started. Let's have a look at my graph as I move the robot. On the graph, notice how as I move the robot, the blue points, which represent the magnetometer, are always just ahead of the orange points, which represent the angle variable. It takes a few iterations through the loop for the orange points to catch up to the blue points. That means that if I turn the robot quickly, the robot is less responsive. It stops pointing north for a time, but then gradually moves back to pointing north. Let's see what happens if I swap these scalar values in my angle equation. This sets the angle to mostly what the magnetometer reads, with less concern about what the old angle was. Now, as I move my robot, you can see on the graph that the points stay much closer together, and my robot is much more responsive to the fast changes in direction. Cool. For more videos, projects, and product information, visit pitsco.com/FABLE.